Okay, we'll get started. Thanks for being here in the room, and thanks for joining us online. If you're joining us online, we are really pleased today to have Dr. Deon Knights joining us, who's come up the road from Vassar. Dr. Knights has joined the faculty of Vassar in the relatively recent past, so he's a new member of the Hudson Valley research community. His research looks at sort of groundwater, surface water interactions and their effects on biogeochemistry and some other things as well. A lot of focus on places where different kinds of water come together. So groundwater, surface water, river deltas, and so sort of hydrologically complex places. Dr. Knights has also been involved with the MHES program, the program that the Carey Education staff runs, looking at mentoring in environmental science for high school students in the Hudson Valley, and mentored a team of students, I guess, this past year. So the education department and the aquatic folks here all had interest in trying to get him into the room and talking to us, and part of the Carey community now that he's here. So we're really glad he was able to make the time to do that. I'll turn it over to Dr. Knights in a second here. I guess I should say to the folks online, if you have questions as we go along here, please drop them into the Q&A section of Zoom there, and we'll be able to take those questions at the end. So with that, thanks, Dr. Knights. Take it away.
Okay, thank you. It's really nice to be here with you in person. I'm really looking forward to giving this talk and chatting with a few of you later on this afternoon. So I was messing around with my slides this morning, and I realized that the title could be changed a little bit. Instead of nutrient processing in coastal freshwater deltas, it could be nitrate processing. It just so happens that I'll be talking a lot to you about nitrate, particularly, as opposed to all the other types of nutrients. I have this picture here. I like to have this as my cover slide. This is a photo of a scene in the Wax Lake Delta in southern Louisiana. And I like it because it shows how diverse deltas can be, ecologically diverse, hydrologically, morphologically diverse. And nitrate tends to move around in a system like this from the hydrosphere to the biosphere, in the plants, the sediment, the water, in all sorts of fun different ways. And the net result of this most of the time is nitrate removal or nitrate retention. So the amount of nitrate that leaves the system, like this delta here, is usually less than the amount of nitrate that gets in. And it was mentioned that I was doing the Mid-Hudson Yes program this summer, and a phrase I used was a bioreactor. So deltas tend to be bioreactors in terms of nitrate removal. So what I'm going to do is the next few slides, I'm going to sort of set the stage, some background, nothing too groundbreaking, and I'm kind of going to lead up to paint a picture of who I am as a researcher. And then we'll talk about two deltas, and we'll get into some methods and some fun results of two different systems. So nutrients derived from human activity are released to the coast. And it's done by basic things like agricultural practices with excess fertilizers and the burning of fossil fuels. And there are even some indirect ways where human influences can increase the amount of nutrients getting to the coast. With rising temperatures and thawing permafrost, you tend to have a lot of organic matter trapped, locked away in permafrost, and even some inorganic solutes that's immobile. But with thawing permafrost, it becomes more labile, and it gets transported towards the to the ocean. And some nutrients infiltrate the soil and are transported towards the ocean through aquifers and and they discharge as direct groundwater discharge. Some nutrients are intercepted in rivers and are transported that way. And in fact, fluvial processes are responsible for transporting a massive amount of nutrients to the coast. And some estimates indicate that up to 1.6 million tons of nitrogen is transported to the Gulf of Mexico through the Mississippi River network annually. So it's a lot of nutrients just through rivers. And excessive amount of nutrients at the coast can have negative environmental consequences like the development of harmful algal blooms. And they're also associated with ocean biogeochemical cycling. This is a picture of a photo of a figure of the Arctic Delta showing primary productivity that's pretty low in the center of the Arctic Ocean, but it ramps up as you approach the continent. Fun fact, the Arctic Ocean is the smallest ocean, but it receives the most amount of riverine discharge per ocean volume. So the amount of river influences has a really strong, disproportionately high impact on Arctic Ocean biogeochemistry. But the transport of nutrients to the coast through rivers, through groundwater is not that straightforward. You can have, for example, let's take the case of phosphate. You could have phosphate being sorbed onto sediment. You can have nitrate being removed through processes like denitrification. So the amount that enters whatever system is not necessarily the amount that makes it to the coast and ultimately discharges to the ocean. And coastal systems like deltas and even these, coastal aquifers have been historically understudied, and they're pretty complex. In the case of direct groundwater discharge, water discharges below the level of the ocean, and you can't see it. It's very diffuse. It's very difficult to get measurements on any spatial scale that's representative of a basin. Deltas are extremely complicated with divergent flow paths. And that brings me to my research interest in general. Broadly, I am interested in understanding nutrient transport and transformation in groundwater and surface water in these complicated and under-monitored coastal systems. So as I mentioned, we'll talk about two systems. Well, one, river-dominated deltas. I don't know why I put coastal aquifers up here today, because we won't be talking about coastal aquifers. We will be sticking with deltas, but the theme is going to be subtropical deltas right here in the Gulf of Mexico, and then we're going to move on up to the Arctic. So I said I've been talking for 20 minutes. I was like, I have not been talking for 20 minutes. Yeah, it's 8 minutes. Okay. Okay. Okay, here we go. Okay. So we have I'm gonna do one key point per region. So for the subtropical delta, I'm gonna give you the key point up front, no mysteries. I'm gonna try to show you that higher elevation ecogeomorphic regions contribute most to nitrate removal, but delta scale removal is likely limited to only a few percent. So that's the end goal. That's what we're gonna get to when we're talking about subtropical deltas. I'm going to have two research questions. I just have one up here for now. So the research question here is, how are nitrate removal rates spatially distributed across ecologic zones? So as I mentioned, the study site is in Wax Lake Delta, which is just west of the Atchafalaya Delta in southern Louisiana on the Gulf Coast. It's actually a man-made delta. The Army Corps of Engineers constructed this channel, and the delta grew from the 60s, I believe, to today. So it's a fun place for studying delta behaviors. The entire delta evolution has been taking place in human observable time points. So I wanted to understand how reactivity varies across different zones on this delta. And in order to do that, I set out I deployed a series of open atmospheric benthic chambers across the delta. And this is an open atmospheric benthic chamber. And it's essentially a fancy name for a 55-gallon drum with the top and the bottom cut off. And what you do with these drums is you isolate a body of water, and then you have this mesocosm where you can sample water chemistry from it with time and observe how nitrate is being processed over time. So we did this on Mike Island here of the Wax Lake Delta here at 5 main study sites. Within each study site, we had 6 benthic chambers deployed at once. And we categorize the delta by 3 different ecogeomorphic zones. We have the upper zone here, which is subaerial. You can see these large woody trees growing here. My colleague who was at Indiana at the time is standing on the delta levee. And I have this upper zone sort of grayed out here. Then we have the intermediate zone, which is right at the interior of the islands here, adjacent to the levees in this sort of dark gray color. And you can see this 4 benthic chambers in the background here. And it's flooded about 80 centimeters or so of water. And you have these floating type vegetation that tends to dominate. And then in the lower ecogeomorphic zone, the vegetation tends to disperse, it gives way, it's more open, and there's still some vegetation as well. That's this sort of lighter green color here, and it's the channels as well as really the interior of the islands, and it starts to get a little bit deeper here. So what I'm showing you here are 2 examples of the data from the 2 different ecogeomorphic zones. I have the intermediate zone and the lower zone. And I know earlier on I said 3, there was the higher, intermediate, and lower zone. We are not including the higher ecogeomorphic zone for right now because it's subaerial and the benthic chambers don't work in subaerial regions. And I would love to figure out a way to sample that in a representative manner so we can get more data and expand this model. But for right now, we have the 2 zones. And what you'll see is, so we're out here on the Delta in July in Louisiana, and we are sampling from just after 10 a.m. to 6 p.m. This is time on the x-axis here. This is normalized nitrate concentration in black. And red, we have chloride. So what you want to see is a decrease in nitrate concentration relative to chloride, which would be the conservative trace. And that indicates that you have some sort of real biogeochemical processing as opposed to dilution or something else taking place. And if you take the natural log of the slope here, you can get a first order uptake rate constant in units of per hour. And you can get a mass transfer velocity in millimeters per hour if you multiply by the concentration. So I'm gonna take a little pause right here, and I'm gonna say a couple of things. So I mentioned this kind of earlier on about, the delta being, bioreactors and stuff like that. There's a bunch of different processes that occur. You may have denitrification, which is, essentially microbes use a nitrate to breathe, essentially, and they produce a nitrogen gas. You can have plant assimilations, so plants taking up nitrate and accumulating it into its biomass. You could have dissimilatory nitrate reduction to ammonium. Nitrate being converted to ammonium, and then it can be converted back to nitrate through nitrification. and many different other processes that change nitrate to different forms, ammonium and nitrogen gas, organic nitrogen, all of that, and back again. The benthic chamber experiments, what I'm interested in is the net nitrate removal. I'm not interested in all the individual pathways. So if you have more denitrification and nitrification and you get a decrease in nitrate, I'm interested in that for this experiment. So that's what the benthic chamber is good at, just getting that net nitrate removal. What we did as well, we measured pH, dissolved oxygen, and temperature for the chamber water measured in, which is represented by the X, as well as the surface water outside. And the idea here is to make sure that what we're measuring in the chamber is representative of what's outside the chamber. So we're not introducing any artificial bottle effects with the mesocosm. And we see here, so this is just a check, we see here that the chamber water and the outside water kind of trends pretty closely. So we feel confident that we get in a pretty representative sample. But I sort of kind of mentioned that we are sampling again from 10 a.m. to about 6 p.m. in July in Wax Lake Delta in Louisiana. And this is extremely, if that statement isn't convinced, this is extremely energy intensive, time intensive. It's very tough work. You sloshing around in mud and stuff like that. Battling the alligators, we saw a couple of them. The mosquitoes and all of that, drinking a gallon of water a day just to stay hydrated, although it's humid. But, and all of that just for one processing rate. One chamber gives you one processing rate. So that's not ideal for really upscaling, right? You can't do that across the entire delta. It's not realistic. So one of the goals, that's fun to go out there and do that. But one of the goals of this study is to see if we can find a proxy for nitrate removal rate that doesn't require you to go out there and do all of that just for one removal rate sample. So we measured a bunch of other things, such as NDVI, which is a greenness indicator, nitrate concentration, grain size, bed elevation, water depth, and sediment loss on ignition. And the idea is to see if we can come up with some sort of relationship with a variable that is more easily measurable than going out there and using the benthic chambers. So it just so turns out that that NDVI and nitrate concentration is a pretty good predictor of VF, which is that nitrate removal rate. And that's pretty exciting because VF depends on, so nitrate removal depends on a remotely sensed metric, NDVI. And that's exciting. So that means that we can use remotely sensed data to give us some sort of an idea of what processing rates are going to be like on Wax Lake Delta. And we were able with that data, with this multivariate regression model, come up with an expansion. So what we're looking at here is we have potential removal on Wax Lake Delta. Discharge flow is from north to sort of southwest here. These are the different islands. This is Mike Island that we studied. The gray here is the sub-aerial regions that were blacked out. But we're starting to see a trend here where we have high removal rates. So the highest removal rates are right near the apex of Delta Islands, and the lowest removal rates are in the channels and sort of as you go southwards and the elevation decreases. So what does that mean in terms of ecogeomorphic zones? It means that the intermediate zone experienced 2 to 3% removal of nitrate, but it takes up 33% of the delta that we looked at. The lower zone, 1 to 1.3% removal, but 66%. So The intermediate zone is half the size of the lower zone, but it removes twice as much nitrate. So relatively speaking, our intermediate ecogeomorphic zone is a geochemical hotspot for nitrate removal. That's this highlighted pinkish region here. But you're starting to see already that there's not that much removal anyway. We're talking about less than 5%, about 3%. So hotspots coincide with intermediate elevation areas. So research question 2 is, how does delta morphology influence nitrate retention in river-dominated delta? So right now we looked at Wax Lake Delta. We had just the one delta. We have different ecogeomorphic zones, but we had the two. And we're seeing here that the hotspots are that higher elevation area. What about different deltas? What about different morphologies? And we're going to start to answer this sort of less than 7% question here. So for this, I turned to numerical models. I worked with some colleagues who came up with a two-dimensional numerical model of Wax Lake Delta. You have flow coming in from the top here and going towards these bottom blue boundaries here. And what I was able to do was, with my multivariate regression model, I was able to map reactivity on top of this based off of elevation. We saw that relationship with elevation from our field experiments. And what we see in here is nitrate concentration about just about 1 milligram of nitrogen per liter coming in. And it stays that way in the channels. So the channels aren't doing much for nitrate removal. But once you get to the islands, that's where you see right near the apex of islands, you really get a nitrate removal. And we saw that out in the field as well. When we were standing in that higher ecogeomorphic zone, it's essentially, I call it squeaky clean. You could probably drink it. You don't want to drink it, but you could probably drink it, I guess. And then once you get, a little thought what's in the islands and in the channels, that's where you start to get the high nitrate concentrations. And then what's really cool with these models is you start to see the effects of tides here. So at low tides, you get when flow is pretty much down on the islands, you have really low concentrations. But once you get high tide, so high tide comes in from the it slows down discharge, and it sort of floods the islands a little bit. What we're seeing here is high concentrations on the island because reactivity is not able to keep up with transport. And we could calculate about a 5.2% removal on Wax Lake Delta. But again, that's still just the one delta. So we really starting to, now I'm going to transition again away from Wax Lake Delta, but that was the modeling framework that we used to come up with some synthetic models. So again, working with colleagues who were able to come up with these computer-generated deltas. And it's important to know these deltas were made in Delft 3D. In this case, flow is from the bottom here to the top. And what's important to note about these 6 deltas is that they were all created using the exact same parameters except for grain size. So by varying the grain size distribution, you vary the friction of the grain size, and it's able to come up with very different, morphologically diverse deltas. So we have this framework we have the 6 deltas. We have an understanding of how removal is supposed to vary with elevation or with ecogeomorphic zones. So now let's put those two things together and see how different deltas react to nitrate forcing. So this is what it looks like when you do the water quality experiment on top of it. So we have high nitrate, so nitrate of 1 milligram per liter in dark red, low nitrate in blue, and you can see in different deltas, you get in different patterns of removal. But that's why there's, I put that here just so you can see what it looks like. But in order for us to really kind of take anything from that, we need to analyze it in a different way. And what I'm showing you now is one question that I was interested in is how does nitrate removal, how does a delta's capacity to retain nitrate change as the delta evolves with time, as it grows, right? Is it going to be better or worse? So we have 9 different time points of the same delta growing with time. And what we see here is we have the area of delta for each of the different time points, and we have the percent of nitrate retention. And it's a pretty straightforward relationship. As the delta gets bigger, you get more nitrate retention. You have more delta to retain nitrate, and that's sort of straightforward. But that again is with the same delta, right? One delta growing, the bigger it gets, it's going to retain more nitrate. But back to the question of, the original question, different deltas completely. What we see here was kind of interesting. It's the opposite of what we saw with the singular delta that's growing through time. Now we have different deltas that were created with different grain sizes, so very morphologically different. And we see the exact opposite in that relationship with area. So a bigger area does not necessarily mean that you get in more nitrate retention. Sorry about the y-axis here. That should be nitrate retention. So area is not a good predictor of retention in different deltas. So what can be? For this, I'm going to take a look at the 3 examples right here of, we have 6 deltas, I'm just showing you 3. And I'm going to introduce a term uptake length. So this is essentially, if you can imagine a solute of nitrate kind of like floating around in the water column, being discharged. And the uptake length is essentially the distance that nitrate molecule is going to travel before it is removed out of the water column through one of the processes I talked about earlier, denitrification, plant uptake, or whatever. And it's a function of the transport, so how fast the water is moving, as well as biological activity, how hard it is, how quickly microbes are sucking things up. So a short uptake length essentially means that it's essentially a hotspot, like, more nitrate is being removed. So I highlighted here uptake length less than 4 kilometers in this light blue. And what we see in here for the 4 different deltas, sorry, 3 different deltas, that this light blue area, this area where we have really high, really short uptake lengths, is very different for the different delta morphologies. You have the silt green sediment, just has this high uptake length region right next to the channels, 2 little channels here, compared to the delta that was made with coarse sand, and you have areas with high uptake length spread throughout the delta. This here is elevation profiles for the 3 different deltas. The blue area right here would represent the actual delta. I have green areas representing vegetation relative to sea level. And what we see in here is, I'm just going to fast forward this, is that nitrate retention on the silt delta, the one that is relatively flat, is about 2.5%. And on the delta that was created with very fine sand, the elevation starts to lift up a little bit more, and we've seen a retention of 4.7%. And then on this delta that was created with coarse sand, it's the one with the highest elevation. So the delta that has a better environment for microbial processes, that has a retention rate of 6.7%. So what we're seeing here, instead of, when we're talking about different deltas, instead of that relationship with area, we're seeing a relationship with slope. So as the delta slopes up more, we get more nitrate retention. It's not always the case. You can see there is, a couple, this delta here and this one here have same slopes with different retention rates. So one other predictor of nitrate removal in different deltas would be complexity. So what I'm showing you here is the number of alternative pathways on the x-axis here. And we're looking again at removal on the y-axis. And you could think of the number of alternative pathways as, let's take a look at this blue delta here, the one that was created with very fine, with silt and coarse sand as an example. If you will a particle of water and you're trying to get out to the ocean, you really only have two ways you can go. You can go this way or that way. So this is a very simple delta. It's not complex. The number of alternative pathways is very low. Compared to this delta here, right? If you wanted to get out to the ocean, there's a bunch of different pathways you can take. So what we're seeing here is as the delta complexity increases, retention rate increases. And why may that be the case? When you have a complex delta, you offer more opportunities for a parcel of nitrate to interact with an ecogeomorphic zone that happens to be hot, compared to if you were simple delta, you pretty much just getting shut out into the ocean without that opportunity to really interact with ecogeomorphic zones that might be hot, that higher elevation areas, those higher elevation areas. So what does this mean for wetland reclamation? So I have this figure here. It's probably a little bit dated by now, but it gets the point, where we have on the Gulf Coast projected land loss for the next 50 years. And pretty much all of the Gulf Coast is expected to be, we're expected to lose it. A lot of it, that's in red here. It's a few areas in green and the Wax Lake, the Atchafalaya, the Mississippi Delta that we expected to gain land. So there's a big push for us to try to reclaim some land here. And my argument is, if part of the reason you would want to reclaim land is so that you can increase the buffering capacity of coastal Louisiana or the Gulf Coast from nitrate, then you may want to consider using sediment with coarser grain sizes than smaller grain sizes, because coarser grain sizes are going to lead to ecogeomorphic zones that are going to develop with higher elevation, that's going to sit up a little bit higher above the mean water table and create that environment where you get hotspots of nitrate removal being created. So I just have this D50 represents the median grain size. So for the 6 deltas, we have, as grain size increases here, we have nitrate removal also increasing, R-squared of 0.84. So I hope I showed you that higher elevation ecogeomorphic regions contribute most to nitrate removal, but delta scale removal is likely limited to only a few percent of input, so less than 7%. And the reason that's important to note is that there's been a lot of talk about natural remediation processes for for nitrate and bioremediation. And that's all well and good. Deltas are good at taking up nitrate, but we cannot rely on them to do the job for us. They're only going to remove about 7%. So part of remediation is limiting the amount of nutrients we add into the environment in the first place, right? Our deltas aren't going to be the saving grace. So that was my subtropical delta part, and I'm going to transition to Arctic deltas. And I'm also going to tie my shoelace before I trip. Okay. So we're moving up over here to the Northwest Territories, Canada, and the North Slope of Alaska. So one key point is winter season is responsible for high nitrate removal in Arctic deltas, and hotspots of nitrate removal cluster according to network structure and discharge on Arctic deltas. And again, I guess I like asking the same types of questions. How does channel morphology influence nitrate removal in Arctic deltas? So just to orient us a little bit, I'm showing you here the Colima Delta. Again, very different scales from Wax Lake Delta. Wax Lake Delta was about 2-ish kilometers or so in length. With the scales for this, the Mackenzie Delta is 200 kilometer length. One of the bigger ones, this is the Colima, so a little bit shorter or smaller than the Mackenzie, but but nowhere near the size of it, but a lot bigger than the Wax Lake Delta. I'm going to show you something that's characteristic of a bunch of these Arctic deltas that's different from subtropical deltas in many ways. They're littered with hundreds of thousands of thermokarst lakes that act as bioreactors potentially. And we're kind of running into the same problem as with the Wax Lake Delta, or similar type of problem where now instead of battling alligators and trying to get one benthic chamber samples, now you're battling polar bears. So it's an environment again where it's remote, it's harsh. To get up there is expensive, and you really you can't get these field measurements all that easily. So again, I try to think, how can I get something that is representative? And I don't want to back up a little bit here before I go too much further. In the case of the Gulf Coast, we have a pretty good idea of how much nitrogen is getting to the Gulf Coast, right? That's relatively easy to measure. In the case of these Arctic deltas, we have about 6 or so of the main watersheds, 4 in Russia, 2 in North America. These red dots highlight gauging stations, and so you could essentially take river discharge and you can multiply it by concentration. You can get an idea of flux that gets into the Arctic Ocean. The problem with that, my argument is, especially look at the Lena Delta. This gauging station is hundreds of kilometers upstream of the discharge point. My argument is what you're measuring going into the delta is not what actually makes it out into the Arctic Ocean. So we have a good idea of what goes into the Arctic Ocean, and we use it as kind of proxies for this is the amount of phosphates, nitrates that particulates that get into the ocean, but we don't really know because of these deltas that stand in the way. So I'm going to show you an example with the Mackenzie Delta located in the Northwest Territories. So we have, north is this way, flow is from south to north. We have the Delta inlet right here. This is the gauging station. We have 200 kilometers. if you were in a straight line of delta, but it's, branching channels, you have lakes and stuff like that. And so that's an aerial image. What we can do with this aerial image is you can use some machine learning techniques and you could train a data set to recognize dry areas from water, or more particularly channels from non-channel areas. You can create a binary mask. And then you can make a series of links and nodes from that binary mask. I'm only showing you the links right now, the nodes just for simplicity, but nodes are essentially points that connect two links together. And with that framework, if you know the discharge that's coming in here, you can route water using some simple morphological and hydrological rules based off of channel sizes or widths of the channels to estimate how much water is being partitioned from the inlet out throughout the entire delta. And that's what we've done here. So the darker blue lines represents higher discharge, and the lighter, thinner lines represent lower discharge. So we have, main channel here running this way, but we have a bunch of different smaller channels as well. So we're able to get discharge for the entire delta in the channels. And what you can do, or what I did was, if you have the flow solved, you could solve for removal rate using these nutrient spiraling concept. And I know you really shouldn't have equations in presentations, but I color coded it just to kind of give us just to see what's going into this model. So you could solve for concentration downstream of each link. So I have a little diagram of a link here. So this is gonna occur thousands of times over and over and over for delta. But if you look at one link here, you can solve for the concentration downstream. If you know the concentration upstream, if you know this mass transfer velocity, that's VF that we calculated with the benthic chambers. If you correct for temperature, and the idea is that on colder temperatures, removal is going to slow down, warmer temperatures, removal is going to increase. And if you take into account the hydrologic load, you can give estimates for concentration downstream of each link. Oops, wrong direction. And that's exactly what I did here. In this case, though, we already know that it's difficult to get to the Arctic. So what I did for this was I used the range of common removal rates for similar type systems from the literature to give estimates. And I did that for the Mackenzie Delta. And what you see in here is slightly shift. So north is kind of pointed this direction a little bit, kind of shift to the delta that way a little bit. And what I'm showing you here is relative nitrate concentration. So if you started off with a concentration of about one, relatively speaking, you can get to 75% or less nitrate as you get to branches near the outlet here. What's fascinating, what's interesting about this is at least in the Mackenzie Delta, at least, you're really not getting that much nitrate removal for most of the delta, and all of the action is happening right here near the coast. And that has implications for, as well, sea level rise has implications for this, right? It means that the area on the Mackenzie Delta, at least, that is doing the most work in terms of removal is the most acceptable to sea level rise, right here at the Arctic Ocean boundary. And so we have not just in Mackenzie, there's 5 other big deltas, big watersheds. And I did it a few other times for the other deltas. And you start seeing here, this is Mackenzie here. This is the Lena Delta, the biggest Arctic delta. You start to see that removal or nitrate concentration is variable again according to delta morphology. The discharges for the Mackenzie Delta and the Lena Delta are roughly the same, but now you see on the Lena Delta that is much more better. It's better at retaining nitrate throughout the delta than the Mackenzie, which is, sort of vulnerable right here at the end, right here at the mouth of the delta. And what you could do, I'm showing you more or less the same data, but shown in a different way. Instead of looking at nitrate concentration, what I highlighted was areas where you had more than 5% removal and areas less than 5% removal. And this light yellow here represents the hotspots of nitrate removal. So it's more or less the same data, but instead of looking at concentration and kind of looking at the difference between the dark purple and the yellow, now I kind of just did that for you. And these are the hotspots for nitrate removal on the Mackenzie, the Lena, the Yukon, the Colima, and the Yenisei. And this is really valuable, I believe, in terms of, if you want to get up to the Arctic and you want to get some measurements, you have the whole, let's be simple here. So we're saying, okay, we're not going to Russia. We want to go to the Mackenzie. Okay, it's in North America. We're not, they're not in a war with any country or anything like that. So you can get there pretty easily. Now you have, over 200 kilometers of delta to sample. Where are you going to go sample? You can use this sort of preliminary data to say, hey, I know something about the hydrology. I know something about the concentration. And based off some simple models, I suspect that hotspots for removal are going to occur right here. So if I wanted to land a helicopter at a particular place, I'm going to target these areas. And this is data that, we don't really have something like this that's going to be useful for supplement. Well, we have now, but we didn't have it for supplementing field work that we can use to, ask more detailed questions. One other thing is, these deltas, again, it's not static through time. It experiences winter and summer and stuff like that. So how does nitrate processing in Arctic deltas respond to seasonal forcing? So I have here two pictures of what summer looks like. I took these two pictures here. These are my field colleagues here just hanging out on a lake in August last year. It's pretty pleasant on the Mackenzie Delta. In the winter, this is not my picture. I haven't been there in the winter. These rivers actually turn into highways in the winter, so you can drive on them. The pictures. If you go on Google Earth, Google Map, you can you can go to the street view where the car driving around. There's a vehicle driving on a river, and you can click on it on the Mackenzie Delta. So completely different environments between the summer and the winter period. And what I'm showing you here is I ran, that model, that simple nutrient spiraling model for different seasons. We have annually. So essentially, I took the parameters for the entire year and I averaged it. I averaged the concentration. That was one of the input. The discharge was another input, and temperature. Averaged it, and I came up with this annual this annual retention rate for the Colima, the Lena, the Mackenzie, the Yenisei, and the Yukon in black right here. We have 3 different seasons here. We have winter, spring, and summer. And what I did was I just took all the summer data, averaged it, winter, and spring. And what we see in here is that counterintuitively, at least to me, that winter season, you get the most amount of nitrate retention. And I would think that that should be flipped, right? In the summer, it's more biologically active. You should get more. But what we've seen here, and at least based off of this model, future field work would me confirm this, is that the discharge slows down so much in the winter. It's allowing much more time for activity to occur. So between, for 200 kilometers of channel length, traveling very, very, very slowly, you are getting some processing. Processing doesn't shut down completely in the winter, it just slows down. So what we're seeing is that the winter months are the winter months do the most work for retention in Arctic deltas. I'm going to, for the sake of time, this is more or less the same same information. I have more time points. Instead of averaging it, I have all the data that I can get for winter, summer, and spring for all the deltas. And the takeaway for these slides here, just take a look at the Yukon here, is that the range in retention for all the years that I have data for the winter is the variability is less than the variability between different seasons. So we are seeing a real signal between the winter, the summer, and the spring, at least for a few deltas, not so much for the Yenisei. And the last two things that I would leave you here with is some projections. What does this mean for future climate change, right? We know that, the Earth is warming, the Arctic is warming, and what we're going to get is increasing temperature. That's the same thing as warming. And we're also going to get increasing discharge. So I ran a model using discharge that predicted discharge increasing for the next 100 years, as well as increasing temperature increasing temperature for the next 100 years. And what we're seeing is, the idea is that you're going to get warmer temperatures. So that's going to probably have, if the only thing you're interested in is processing, then increasing temperature would be a good thing if that's the only thing you're concerned about. But you're also going to get increasing discharge. And if the only thing you're concerned about is processing, then increasing discharge is not a good thing for nitrate retention. So we have a sort of battle between, projected temperature increases and projected discharge. And what we see in here, so this is our current, let's just take a look at the Mackenzie right here. So this is our current retention value right here. And as discharge increases, you're going to get decrease in retention. And as temperature increases going up, you're going to get increase in retention. But the net effect of that would be when you combine higher discharge as well as higher temperature, you are going to get net reduction in retention. So overall, if you combine temperature and discharge data, projected climate change is not a good thing for the delta's capacity to retain nitrate, at least in the channels. The last thing I'm going to say here is, I talked a lot about the channels after I said how deltas are littered with hundreds of thousands of thermokarst lakes. Here they are, highlighted here in this amber color here for the Mackenzie Delta. The green little blobs here are all the connected lakes, or lakes that are connected to rivers. The orange ones here are kind of all the lakes present. The next step is to try to integrate with the methods that I'm using all the water that is in the lakes with channels to see how much of an influence these hundreds of thousands of thermokarst lakes have on retention in Arctic deltas. So just to highlight the key points again, I hope I showed you that in subtropical river deltas, that higher elevation ecogeomorphic regions contribute the most to nitrate removal, and deltas that sit up a little bit more, a bit more efficient at removing nitrate. But all in all, deltas aren't going to be our saving grace. They only retain about 7% of the amount of nitrate that we add currently. In Arctic deltas, I hope I showed you that remotely sensed data provide a useful tool for revealing patterns of nitrate retention in the Arctic in a region that we can't readily access. The channel networks of Arctic deltas are most efficient at retaining nitrate in the winter. We don't know about the lakes quite just yet. That is work that hopefully I will get to do soon. And this work was funded by a bunch of organizations from GSA to NSF. I work with a bunch of colleagues from Vassar to West Virginia, Delaware, Ohio State. This is my field crew out in the Waxlick Delta. And I will stop here and ask for questions.
Well, thanks, Dr. Knights. I learned just before the seminar that Dr. Knights has a new baby who was born 5 weeks ago or something like that. So it was sort of a superhumanly good talk for somebody who's presumably sleeping about as much as he is. And I was very relieved actually that his shoe was untied for a little bit there, because it was at least a little signal of like not having everything quite fully together. But great talk, and we'll take questions. Alan.
Your winter retention, the flow is lower than kind of over the whole annual cycle is still more kind of total retention happening in the warm season, or how's it add up on kind of an annual budget of rather than percent of like the total?
Yeah, no, that's a good question. So oh yes, sorry, yes. So the question was, so we're seeing that for winter months, it's a higher percentage removal, but what does that look like in terms of like the actual mass of nitrate removed compared to the other seasons? And it's also higher in the winter in terms of mass removed. And part of that is because for reasons that I don't have the best explanation. I haven't really seen a fantastic explanation of why the concentration coming in the winter months are a lot higher than in the summer. So the mass retained is a lot higher as well compared to the summer in a more absolute sense than just percentage.
Go ahead, Jess.
Okay, so in your studies in the subtropics, a lot of the sort of effects of geomorphology have to do with interaction with vegetation. So I'm curious as to what you think the role of vegetation is in your Arctic deltas, and what you think that role will, or how do you think that role will change given things?
Yes, yeah, no. So the question was what in the subtropical deltas, vegetation seems to have a big role on retention, and what would that role look like in Arctic deltas? So, so I think it's a couple of things with vegetation. I think sort of like the biggest go-to is, well, more vegetation means more plant assimilation, conversion of inorganic nitrate to organic nitrogen. But what I think is a big factor as well is just the vegetation biomass itself, the detrital matter that forms, sort of anoxic microsites that just debris in the water column that tends to have places where microbes can hang out on and create these anoxic conditions. So I think in the Arctic, you're going to get a similar response where you have just a bunch of stuff. So you're going to areas where you have a bunch of vegetation, you're going to see higher removal as well. But you're not going to see such a strong signal in terms of plant assimilation, especially where they warn me that this is going to happen. I want to go back right here. We could use this area here. So because let's just focus on the Mackenzie for right now. Because it's so big, you're moving into just different climates essentially. So right around here-ish, even midway through the delta, you're still in, kind of like, boreal region. And only until you get out here, you get tundra. So the vegetation is going to change drastically. And I think out here, you're not going to see that much of a relationship with vegetation or NDVI in a way that you would see up here. That's simply because the vegetation is completely different. There's just not that much stuff growing in the Arctic tundra, essentially.
We might have time for one more quick question. Sarah, did you have one?
What you found was that the majority of the nitrate retention was at to the edge of the Kentucky Delta. What caused that? Why was there like so little flexibility on it again?
And then like right at the end here. I think the biggest driving point for these patterns of retention right now is hydrology. I think that and in fact, I think that's the story right now, at least with using literature values for processing rate. When you have so the question was what why we have high retention near the end of the Mackenzie and not so much upstream. I think really these rivers are vast. They are ginormous, and you just have high discharge flowing all the way downstream until you get to some of these smaller channels here. So I think it's that there's a battle between, I mentioned earlier with nutrient spiraling, there's a battle between transport and processing. And I think that transport is just too fast for most of the Mackenzie for processing to keep up with it. And only when you get to smaller channels near the end, that's when you can get processing having some sort of a influence on rates. In a way that's different in the Lena Delta, where you do see a lot of these small, this channel here is really big, and this guy here is really big, but then you have a lot of smaller channels here, and there you get a chance for processor to have a chance of taking up some of the nitrate.
Okay, we should end it there. Dr. Knights will be joining us for lunch. So if you're here in the building and wish to continue the conversation, please do. And there's also an open discussion with the education staff and anyone else who's interested at 1 o'clock. So we hope you'll be able to join for one or more of those things. But let's thank Dr. Knights again for a great seminar.
Thank you.